Welcome to this tutorial on solving the eigenvalue problem for a mass spring damper system using OML, the Open Matrix Language. In this video, we will learn what eigenvalues and eigenvectors are, why they are important in engineering, and how they help us understand the dynamic behavior of mechanical systems. We will then walk through a complete OML program that calculates the eigenvalues and eigenvectors of a mass spring damper model. Even if you are new to control systems, state space modeling, or vibration analysis, this example will provide a practical introduction to these concepts. By the end of the video, you will understand both the mathematics and the code behind the solution. Before looking at the code, let's understand the theory. Eigenvalues and eigenvectors are special properties of a matrix. When a system is represented in matrix form, eigenvalues reveal how the system behaves over time. They can tell us whether a system is stable, unstable, oscillatory, or damped. The associated eigenvectors describe the directions or modes in which the system naturally responds. In mechanical systems, eigenvalues are closely related to natural frequencies and damping characteristics. If the eigenvalues contain imaginary components, the system oscillates. If the real parts are negative, the oscillations gradually decay and the system is stable. Engineers use eigenvalue analysis extensively in vibration studies, structural design, robotics, aerospace engineering, automotive systems, and control engineering. Understanding eigenvalues allows engineers to predict how a system will react before building a physical prototype. The mass spring damper system is one of the most fundamental models in engineering. The mass represents an object with inertia. The spring stores energy and produces a restoring force proportional to displacement. The damper dissipates energy and reduces oscillations. Together, these components model many real-world systems. Examples include vehicle suspension systems, building vibration control during earthquakes, robotic actuators, industrial machinery, aircraft landing gear, and many other mechanical structures. Engineers analyze these systems to determine stability, vibration levels, settling time, and resonance characteristics. Eigenvalue analysis provides a quick and powerful method to understand these behaviors directly from the mathematical model. Now let's examine the OML program step by step. The script begins by clearing the workspace, command window, and any open figures. This ensures that previous variables and results do not interfere with the current calculation. Next, the physical parameters of the system are defined. The mass, represented by m, is assigned a value of 2 kilograms. The damping coefficient, represented by b, is assigned a value of 2 newton-seconds per meter. The spring constant, represented by k, is assigned a value of 2 newtons per meter. These values completely describe the physical characteristics of the mass spring damper system. The program then constructs the state space representation. State space modeling converts the second-order differential equation into a set of first-order equations. The matrix contains the system dynamics and is defined using the mass, damping, and spring parameters. The B matrix represents the system input. The C matrix specifies the output relationship, and the D matrix represents direct feed-through, which is 0 in this example. After defining the matrices, the command SS creates the state space system model. This gives a compact mathematical representation suitable for analysis and controlled design. The most important step follows. The Eig function is applied to the matrix. This function calculates both eigenvalues and eigenvectors. The variable v stores the eigenvectors, while D stores the eigenvalues. These results describe the natural behavior of the system without requiring time-domain simulation. The output shows 2 eigenvalues. In this example, the eigenvalues are approximately negative 0.5 plus 0.86603i and negative 0.5 minus 0.86603i. Notice that the eigenvalues are complex conjugates. This indicates an oscillatory system. The imaginary part corresponds to the oscillation frequency, while the negative real part indicates damping. Because the real parts are negative, the oscillations decrease over time and the system remains stable. The eigenvector matrix contains the corresponding mode shapes. These vectors define the characteristic directions in which the system naturally evolves. While eigenvalues provide information about stability and frequency, eigenvectors provide information about how the states participate in each mode of motion. Together, eigenvalues and eigenvectors provide a complete picture of the system dynamics. Instead of running lengthy simulations, engineers can immediately evaluate system behavior using eigenvalue analysis. A positive real part would indicate instability. A zero real part could indicate sustained oscillation. A negative real part indicates stability. Large imaginary parts correspond to faster oscillations. These insights help engineers modify system parameters such as mass, damping, or stiffness to achieve the desired performance. For example, increasing damping generally moves eigenvalues further into the negative region, reducing oscillations. Changing the spring stiffness affects the natural frequency. Such analyses are critical during the design phase of engineering projects. In this tutorial, we explored the eigenvalue analysis of a mass spring damper system using OML. We learned what eigenvalues and eigenvectors represent, why they are important in engineering, and how they are used to study system stability and vibration characteristics. We examined the state space model, created the system matrices, and used the Eigen function to compute the eigenvalues and eigenvectors. The resulting complex eigenvalues showed that the system exhibits damped oscillatory behavior and remains stable because the real parts are negative. This simple example demonstrates a powerful engineering technique that is widely used in mechanical engineering, control systems, robotics, aerospace, automotive design, and structural analysis. Understanding eigenvalues is a key step toward mastering dynamic systems and advanced engineering analysis. Thank you for watching, and see you in the next tutorial.